Newton's first law of motion states that an object will remain at rest unless a force acts against it to move it, and an object will remain in motion unless the force acts against it to change its direction or stop it.
In our first demonstration, we threw a basketball into the hoop, hitting the backboard. In this situation, the basketball keeps on propelling forwards, the throw force, air resistance, and gravity acting on it. Then when it comes into contact with the backboard, the throw force is eliminated, and only gravity and air resistance act on the basketball, forcing it to fall downwards. We can see how this demonstrates Newton's first law of motion, because the basketball would have continued in an arc projectile until the backboard becomes the opposing force, shifting its motion downwards. This demonstration gives another insight into Newton's first law of motion. In this demonstration, we can see the speed differences a bike possesses when affected by the slope of the hill. You can see that when the bike proceeds up the slope, its speed is significantly hindered due to the hill's opposing force and gravity. On the other hand, when the bike advances down the slope, its speed is considerably increased compared to its upwards endeavor. As in this situation, gravity and the slope's force are working with the bike, not against it.
Newton's second law of motion states that an object's force is equal to the object's mass times acceleration. To put it simply, F equals m times a. In this first demonstration, we had one person attempt to transport a TV stand from one side of the room to the other. Afterwards, 4 people sought to move the stand. It was apparent that the stand was able to shift more rapidly when pushed and pulled by 4 people, opposed to just one person. By doing this experiment, we were able to examine how more force equals faster acceleration, giving support to Newton's second law of motion that mass times acceleration equals force. In our second demonstration, a basketball and a ping pong ball were both dropped at the same time. They both landed on the ground at the same time as well. This is because both experienced the same acceleration of 9.8 meters per second squared. The acceleration is independent of mass. Thus, when they were dropped, they will always maintain the same velocity and travel the same distance.
Newton's third law of motion states that for every action force on an object, there will be a reaction force. In this demonstration, we inspected a birdie's motion when it came into contact with the badminton racket. We were able to identify Newton's third law of motion in this demonstration because when the racket is going backwards and forwards and the birdie comes into contact with the surface of the strings, it propels upwards in the arc projectile. This propulsion is in fact the reaction force of the action force, which is the swinging of the racket that produces the racket's force. In this second clip, we all jumped up and back down. This is a demonstration of Newton's third law of motion because in order to propel ourselves upwards, we used our feet to launch us up in the air from the ground. The action force in this is using our feet to propel ourselves in the air, and the reaction force was when we were in the air.
Hey, have you guys seen my phone? I've been searching. Hey, have you guys seen my phone?
In this additional display, it exhibits a person slipping on a banana peel. It shows the reaction as an effect of the action force, which in this case, the action force is a person's weight pushing on the banana peel, while the reaction force is a banana sliding in the opposing direction, causing the victim to fall horrendously to their demise. This situation represents Newton's third law of motion because it demonstrates the effect of an action force, or as Newton would say, the reaction. Go! It's recording! There's 26 minutes on there.
Oh shit.
Go!
Hey, have you guys seen my, Hey, have you guys start.